which is the compact region of the galaxies surrounded by the supermassive black hole, where actually most of the emission is coming from. The second concept is the synchrotron radiation, which is the radio emission from an accelerated charged particle that is moving under a strong magnetic field. Stokes parameters are a set of the parameters that you could actually describe them for the polarization of the electromagnetic field radiation. And then the continuation of the context is, for example, linear versus the circular polarization. As you see here, some images of the linear polarization, and then some of them that are actually the circular polarization, and also the Faraday rotation, that is the rotation that induced in the linear polarization when you have the left versus the right component of the circular polarization move in different rotation. And then that's actually going to happen when you normally have a plasma, for example, ISM, that light from some stars goes to them, for example, you can just say in a way to get to Earth. And then because of that, because of the fact that there are some, basically charged particles that are moving, they would also create some magnetic field. So when you consider the circular polarization, some of the components of the circular polarization would be boosted to be more speedy and the other one would be slower. So at the end of the day, the combination of them would be another linear polarization, but it's slightly shifted with the angle that has something to do with the component of the magnetic field along the actually line of sight, and also the density of the electrons, and so on and so forth. Another concept is the Faraday conversion. That is kind of like similar to Faraday rotation, but here you just compute and just say converts the linear to circular polarization. The former one was just linear to linear polarization. So here again, when you actually have electromagnetic wave that pass through some plasma, you see that kind of conversions. So these are the kind of like very basic actually context that I wanted to basically, introduce to you so that we could just have more of the interaction together. Now let's start with the first item. I told you that we are interested on a study of the jet physics and especially the matter content of the jet. So that brings me to some of the works that we have been doing with my great collaborators, actually, and we are still doing in a follow-ups. So that's about the positron effects on the polarized imagery spectra from the jet and accretion flow of models of M87 and Sagittarius star. I'm not going to mention all of the details today, but I would rather just give you very quick overview of what we have been doing. Let me start with the theoretical motivation for that. As you may know, one of the outstanding issues in the physics of the AGN is the matter content of the jet. It could be either the pair plasma or it could be ion plasma. And it's very important because for those of us that have been studying, for example, me and Kaushik and others, we've been very much actually involved with some jet analysis that I will mention to you later on. And it seems like that the jet is not powerful at the milli-arc second or even beyond that, because you just lose all the powers of the jet. So whether or not they would be powered by some electron versus positron that are going to be actively actually being created around the jet funnel or not, that could be a solution, who knows? And if that's going to be happening, then that's very hard because one needs to come up with really actually dynamical creation of the electron and positrons and evolution and so on and so forth. So that's kind of like the outstanding question to begin with the concept. The creation of the pair may actually involve some levels of the interaction between the jet and photons, for example, through photon-photon interaction that can lead to electron versus the positron in the accretion actually, or in the immediate surrounding. And of course, if you have ion versus the pair plasma, that would affect actually your properties of the accretion of the basically, acceleration and collimation of the jet, and also between the core of the radio emission and also the accretion disk. So that's fundamentally important and life-changing if you consider one way or the other. So that's completely from the theoretical perspective. Observationally, there have been many different studies of actually search for the plasma composition. That could be some VLBI observations through the circular polarization, through the linear polarization, and through the emission line. If you go through, and this is just like a very short of the long actually list of different papers of different studies that use different sources, for example, M87, quasi 3C279, or something like 3C345, or whatever actually 3C120 or whatever else. So in all of them, you see that some of them, they actually are completely in favor of having positrons, while the others put some constraints and so on and so forth. So again, this is very actively evolving field of research, especially observationally, because like what I told you, some of the properties of the jets that we are actually looking for may or may not be that easily possible to be explained by the ion plasma. And then, that actually also motivated us to go for some observational actually signatures of that. Now, theoretically, again, how you could potentially get all of these pair basically plasma to begin with. So pair creation in the jet can happen through many different mechanisms. Every Broderick and Monica and others like Chen, they did a super great job in modeling, proposing some very good actually modeling for the jet, and then for the creation of the pair in the jet funnel through some stagnation surface, or through actually some kind of under basically the jet funnel, or even in terms of having some dynamically actually evolving pairs of the electron versus positron, when you see here that how much different components would actually behave differently. So that's again very actually active area of research. That's a little bit hard to do them from scratch dynamically, using the Geo Chemistry Simulation with having just forcing these electron and positrons to be created, because there would be a scatter, there are some kind of a secondary production of the pairs and so on and so forth. So what can be done that we could at least get some actually sort of intuition without putting too much of the effort at least to begin with? So that brings me to the approach number one that we started with a while ago with some folks, especially Rita and Ansu and Andrew and others, that we have had a lot of cool basically investigations, and I'm happy to tell you about them. So in this approach one, we don't really consider geochemistry simulations to begin with, but we rather consider some semi-analytical marks that are actually coming from some fitting formula to some harm simulations. For example, from McKinney in 2012, actually, from MAC accretion with some black holes of prograde 0.92, and in which we actually present some fitting formula for the magnetic flux, for the angular speed, and for the gas pressure. So in this case,
can you please say what a harm simulation is and what MAC accretion is?
Yeah, so actually the harm simulations are actually one of the, there are some libraries of very well-known simulations that people consider. For example, harm simulations from McKinney, and I'm happy that Richard can also, go ahead.
Emission is high accuracy, relativistic hydrodynamics, and it's a conservative general specific hydrodynamics for solving for the fluid variables, and you can continue this.
Yeah, exactly. So that's had been used extensively by Richard during his PhD when he come up with some kind of a fitting formula that in these works we are actually using them. So in another word, instead of just being worried about the magnetic flux or actually angular speed or pressure or whatever, we just use, imagine that your actually simulations are just giving to some parabolic actually jet. You fit some formula into it and you just try to actually use them. And then you add some formula, you add actually some parameters that are listed here that will be actually mentioned to you, like B naught, for example, or other quantities that I would actually describe in a moment, that are basically our parameters of the model. So we give it some kind of a freedom in terms of the parameters, but rather some of the behaviors of the jet at the larger scales or whatever is not something that we propose by our hand, but rather we just actually motivated from the known simulations that we actually use. And this magnetically arrested disk, it's just coming from Ramesh that did a super great job, in basically having kind of accretions that are with very actually high magnetic field. And I'm very happy that he's here so he can just tell us. And that was a great discovery because as I will describe it to you, she is actually favoring a lot the MAC simulation. So finger crossed, that was super great. And maybe that was the reason that even without knowing that we started with this. Anyway, that was just before the polarization result of the ESG comes to exist. So, okay, great. So actually, so in this note, I'm going to tell you that from here, I'm going to actually use this model. I'm going to actually present some of the basically parameters that we have. So far, we have B naught, which is a dimensionless actually magnetic scaling that you could just scale it. These geochemistry simulations are very much scale free. You can use them whatever you want. And then you can just try to basically fix the B naught, for different sources. For example, in this case, we actually use it. We just fitted this for MAD7, that at 230 gigahertz from the ESG, we have 1.5 Jones speed. So that actually, that basically gives you B naught. But that's not the only parameter of the model. We're also dealing with more of the parameters that are coming from the emission, because like what I told you, when you have some electrons, some charged particles that are under the effect of the magnetic field, they would radiate actually. So you would have some, basically, you would have some synchrotron emission, and then in this case, we just consider some non-thermal electrons that are power law between actually some Lorentz factors of gamma min and gamma max, and some parameters, including P actually, for example, here, and some other actually parameters that would actually comes from the ratio between the electron pressure to be basically to the magnetic pressure. So in this case, I'm not going to go through the details. I'm not really wish to do it, but I want to put you in the context. We have a Geo Chemistry simulation. We got a fitting formula into it. Now we have the plasma that is either the electron or positron or actually or both of them as I will describe. And we want to know how much we could actually potentially model it. In order to model it, we also have to model the synchrotron emission that we use the power law formula for it with P and actually beta that is basically, as I described, this is basically the ratio of the magnetic, of the basically pressure of the gas divided by magnetic pressure. And these are the set of parameters that during this talk, I would actually mostly describe. So now let's proceed. So far we just talk about the simulation and the synchrotron emission. Now let's go further and also consider how much we could get out of it. We know that, for example, for the ESG, we just consider something like imaging. So for that, you really have to ray trace them. So in order to do it, we actually consider the geotrans. Geotrans is actually very nice setup that you could use because all the geo effects, for example, light bending, the lensing of the light, ray tracing are actually naturally incorporated. We can also consider the, the Doppler busting or the emission of the intensities from radiation and so on and so forth. They are all naturally implemented in the code. So what it does is that you actually have a set of Stokes parameters that I earlier, described it to you, including the emissivity, absorption, Faraday rotation, and Faraday, conversion. So these are not the Stokes parameters. I, Q, U, and V are the Stokes parameters, but these would be actually affected by set of the basically emission, absorption, Faraday rotation, and conversion. So to some set of the differential equation, you wish to actually compute the I, Q, U, and V, and then from that, you can just derive the intensity, linear polarization, and circular polarization. So in order to do it, and in order to make sure that all the geo effects are actually correctly incorporated, we use the geotrans code as I already described it to you. And in addition to that, we also made some modifications to the geotrans, in which we also added the impact of the positrons. That is actually this fraction of the basically positron to the electron. So in another word, all of our actually quantities for emissivity, absorption, Faraday rotation, and conversion now see some actually extra basically contribution from the positrons. For example, intensity would be added up basically for I, Q, and U, but for the circular polarization, it would be subtracted. For the absorption, the same. For the Faraday rotation, quite remarkably, you see that when F goes to 1, you are just completely out of the Faraday rotation, but Faraday conversion would be actually added. So let's just keep all of this in our mind because as I will describe, they will be essentially useful for us when we consider the imaging and then actually list up the properties of the image that we see at different limits. So now let me actually go through the results directly. So again, I'm not going to actually put a lot of details into it. What I'm going to tell you is that, as I already told you, there are some source of the parameters associated with our model. For example, positron fraction, the P that was the power law that I actually described, and also the basically the gas pressure divided by the magnetic pressure, that was the beta. So we have a family of 3 parameter space that we would need to consider how many of them would be actually rolled out using the most recent EHT observation. So let me start with those that are not rolled out because otherwise we will be completely disappointed. Let's start with the best bet jet model. So this is actually a set of models. I have to tell you that we considered about even 100 different models. A lot of them, I'm not going to present the table, you're better to see it in our paper, but a lot of them, because of the polarimetry of the results of the ESG, and thanks to all of their fascinating work, that was super essential for basically for running all of these models, they were kind of like completely constrained or completely disfavored by the observation. Only 3 set of models out of that actually, large community of models survive. That almost entirely actually leads to very low fraction of the positron. In another word, when you increase the positron fraction, since the Faraday rotation diminished as 1 minus f, you're actually going to not consider a loss of basically, kind of like disfavor or just like reducing the actually polarization. And because of the fact that we have tight constraints on the linear polarization, they will be completely rolled out. And the same for the Faraday rotation, Faraday conversion, or actually secular polarization. So in another word, for lower values of the positron actually fraction, the Faraday rotation is still very actually important such that it would diminish the linear polarization. And thus you can have a better chance of not being rolled out. So here, for example, you see that when you increase the positron fraction, you can actually see that the Faraday rotation actually is just diminishing, and then you're kind of like enhancing a little bit. That would be through the actually, because these are the same kind of like color bars, you see that this one is actually stronger than the other one. And that kind of like reflects what I was actually talking about. So we see that Q and U are scampering at low positron fraction, and they get regular at higher positron fraction, again, as a consequence of Faraday rotation. So that's something that is good to have. Actually, we are very happy that we ended up at least with 3 models out of 300 or out of hundreds or whatever, and not completely be disfavored. And let me now also mention some of those that are completely disfavored, or if you want roll out. You see that how strange this is. For the full positron fraction, since there is not any Faraday rotation, you extend too much Q, U, and V that are completely rolled out by the ESG observation. So that kind of like conclusion is what we get, that in order to be consistent with our very fascinating ESG observation constraints, we have to be very low in the positron fraction, but it's still not that low. Even 10% of positron fraction could be actually sufficient, but not really more than that. And even that, you see that when you consider the linear polarization, sometimes they go a little bit actually upper than the current stage of the ESG, but we know that sometimes the blurring is not the same. There are some actually, systematic errors and so on and so forth. So we just make the life easy not to get nothing out of the pool. But you see that how hard it is actually when you consider, actually putting all of these models inside the current very concentrated EHD observational constraint. Yeah, please go ahead.
And just to say, don't worry about the high frequency where there's like an optically thin part of that synchrotron spectrum above 10 to the 12 hertz on the left, because we can change the power law index in order to fit that. So, in order to economize the number of dots in the paper, we weren't allowed to, have many values of that P power law index, which would move up that theory curve to through those data points. But we have some models that basically go through the high energy data points in the optically thin part of the high frequency synchrotron.
So basically, the entire spectrum can be fit if you allow.
Yeah, but if you have many complicated models, that wasn't really the aim of this work.
So
but in principle, yes, yeah. Kaushik, yeah.
Actually, you're not supposed to fit that part because it's supposed to come from the larger phase component.
That's another saving grace, but if we,
I think a model said that.
but if you are worried about it, we kind of just said high frequency or by the P.
Yeah, thank you so much, Richard. That was a great point. All right, so actually, at least we are having 3 different models that are doing relatively good works, as you can actually see them here. And something which was remarkable is that when you consider the basically secular polarization, you see that their actually behavior would be very much actually different or very sensitive to the positron fraction. In another word, when you consider the positron fraction to be 1, you see that at actually higher frequencies, there are some declines of the secular polarization, but at the lower frequency, this is not. So that actually tells you that if someday we could collect all the data and we could just combine them together and go for some posterior analysis or whatever, we may just get even better actually chance of putting constraints on the models. But again, that wasn't really the purpose of our actually analysis. We wanted to write for EHD and we just focused on 230 gigahertz, as our friends actually did a great job of actually putting this constraint. So now let me go further. I told you that a lot of these models are rolled out, but how? For example, this is beyond the best fit models, in which, for example, you're considering to increase the value of the beta. Again, beta was the fraction of the gas pressure divided by the magnetic pressure. So as you could see again for the same color bars, the ones that actually consider very low values of the beta, they do have a very less actually reduction of the Faraday rotation. And because of that, the linear polarization would be much, much higher than those that are actually having larger values of the beta. That's the reason that they would actually get rolled out. You can actually also consider those in terms of their spectra. And again, as you see, they are much above actually what you could potentially see. So that's the reason that they are rolled out. You can actually also consider another set of models that in this case, you're considering the beta in knots for the spectra, right? So now let me go further. Okay, I think that that's actually the last one for this slide. You can actually see that how they are going to be different. And of course, there are a lot of details that I'm not going to go through them because there are more things to discuss, unless you have any other question. So that brings me to the, okay, perfect, go ahead. Yeah.
So maybe naively, but you seem very disappointed with that you rule out so many models, but that sounds very positive to me. Sounds like you kind of have some evidence for that indeed the positive fraction is lower. Is that like, is there some other reason why you're not satisfied with this? Is the model too complicated? Or
no, I mean, I'm not saying that I'm not satisfied with it. It's just the real, right? It's just the truth. It's just the nature that decide whether they want your positron to be fully dominate, the jet or whatever or not, right? So, but then that's a great question. That's a great point in a sense that yes, we are actually not completely running out all of the models with positron. And that's essential because like what I told you earlier, for the jet, we have a lot of problems of actually explaining the jet in very, very, very long, basically, extension. And maybe one possibility is that you're going to cover those jets with the pairs of the positrons and electrons, right? So in another word, the fact that we are not completely roll out all of the models is a good thing, right? You may even want it to be actually not to be that much constructive to begin with, like 50 or whatever, but that's not something that MAD7 would allow us to do actually. And it's even worse for Sagittarius star. In our analysis, we showed that it's almost completely actually disappointing of having any positrons there. So MAD7, it was just, the best thing. And of course, we know that MAD7 has a very much pronounced jet that Sagittarius star doesn't have. I'm not going to go too much and make the connections that may or may not be true, but I'm just making a proposal that maybe having a positron is a good thing to do something at long jet and so on. But finger crossed, let's just stop here. And I'm very conservative not to say something that I haven't tried, but maybe that's actually something to go for. So I'm going to actually.
Great question. So
please,
adding another frequency really be very important.
Okay.
230 gigahertz. Is that what is going to be that will lock in the best class of models?
Very nice. So I should tell you that 230 gigahertz just comes from the surrounding part of the black hole, right? As ESG was actually doing a super great job on this kind of measurement. There are also some other frequencies like 86 or 43 or whatever actually lower frequency that if you consider them, you go further and further and further out from the central part of the black hole. So I'm not really sure. I mean, I'm very happy that some of the observers like Shep are actually also here. So maybe there are already some good observational constraints for the polarization for that frequencies. We haven't really used them, but that doesn't mean that they are not existed. But I mean, if somebody has any actual comments, please speak up. But in summary, I'm going to tell you that for us, that was kind of like a very well motivated question to begin with, because we wanted to consider the imaging and a spectra of those that are actually located next to the black hole in terms of the accretion and so on. And then, ESG was the best frequency to go for. But yeah, please go ahead.
Razieh, if you go a couple of slides back and you see that spectrum where the circular, one more. Well, there's a major splitting between the circular polarized spectrum on the right, where we have the highest frequencies. The circular polarization spectrum falls much more rapidly with high positron fraction at high frequency than with lower positron fraction. And this is like a telltale sign. So you see those like at the right, there's a red curve and then there's a turquoise curve that are practically on top of each other. And those are for the relatively low positron fractions. But when you get to the high positron fraction on the bottom, you just aren't able to create enough circular polarization in the symmetric pair plasma that's represented by the highest positron fractions. And that makes this signal very strong. So if we had the observations at the higher frequencies,
it would be a real discrimination
yes,
between low versus high.
Yeah, absolutely. You're right. But in terms of the actual observations, that would be really great to look for afterward, because of course, for example, in terms of intensity, we have been collecting all the data also from actually this part of the spectrum, but for the linear and circular polarization, we haven't yet. But we could potentially consider that, and that's a really great question. Okay, now let me now actually proceed very quickly and consider approach number 2. I started telling you that it's very hard to go for some kind of modeling of the positrons from scratch using the Geo Chemistry Simulation. We started with completely semi-analytical models. Now, as a continuation up to that, you can go one step further and you can consider not completely to be actually semi-analytical models, but you could consider math versus the same simulation as you actually see them here and just increase the positron fraction. So in this case, we are actually using the home simulation from library of the Geo Chemistry Simulation from Illinois that is very common to use for the ESG collaboration. And we are just increasing the positron fraction. So my only takeaway, and that's the work that Richard actually is just leading currently. That's very interesting because that actually tells us that for the mass simulation, the EVPAs don't rotate too much. And I will actually go back to it, in a moment, into actually the second topic that I will describe any momentarily. But for the same simulations, you actually see that EVPAs are actually very much rotating. So that's kind of like the things that one needs to consider when you consider, for example, circular polarization. So again, let me just be very quick and go for the other few basically topics that I wanted to describe. So the second topic that I would actually rather quickly describe it is linking the polarizing actually image of the synchrotron emission to the magnetic field structure. So you see that here, there is some actually emission basically profiles that I will describe what do that mean actually, what do I mean by that, or what does that mean in a moment. But let's just keep it in mind that actually has something to do with the proximity of the supermassive black hole when you actually consider where does the most majority of the emission is coming from. That are actually shaded with this whitest basically dashed region around the supermassive black hole. They happen as a mutually average over. So then you have a different snapshot of your Geo Chemistry simulation, really determining where does the emission come from. But why this is useful? Let me open up the context again. So as you know, and as you have actually already seen so far, synchrotron radiation from hot plasma, like electrons that are orbiting to the supermassive black hole, like a spinning supermassive black hole, creates some polarization, some polarized image. This is very common to expand this polarization in terms of the beta M coefficient, thanks to the actually Palomo work in 2020 and afterward, that parameterization has been extensively used by the ESG collaboration, in which you actually expand the linear polarization in terms of beta M coefficient, and EVPAs are actually half of the phase of this linear polarization. So I'm going to tell you that these forks actually show that beta 2 is the dominant mode of the linear polarization. And owing to that, hereafter, I just restrict myself to the beta 2. So again, no actually confusion. This is beta 2. This is the phase of the linear polarization expansion. And we are going to use that. But why this is so essential? Because this image polarization is actually basically determined by many different key effects. For example, magnetic field actually geometry, velocity field, black hole spin, polar transport, strong lensing, and so on and so forth, which are very much complicated to understand and basically numerically. So how we could potentially link them together? Ramesh did a super great work in an official paper by the ESG in which he actually collected all different effects, completely analytically, completely semi-analytically, and just try to understand what's going on in terms of whether math or SEN are going to be favored and so on and so forth. So motivated by that, in the next couple of slides, I'm going to compute beta 2, complex actually beta 2 that I just described, using Geo Simulation, completely from the numerical perspective. And I would love to consider comparing this with the semi-analytical works that Ramesh and actually Narang et al. Did in 2021 through an official paper, and that was also continuous. So that was for a case of non-spinning black hole. And Gilles et al. In 2021, they considered this actually as an extension to also consider the spinning black hole. So from here, so on, I'm going to compute the beta 2 from the numerical simulation, and I'm going to compute and just actually compare that with the results from the semi-analytical work. So I hope that that's kind of like clear what I'm going to do, because I'm going to be super fast here. Let's start. This is the Hammer simulation. This is the harm simulation from math versus the same. Just one particular case of a spin of black hole to be minus, minus prograde or minus 0.94 across different times. And as you see, EVPAs that are actually these basically green lines here are going to tell you how do they basically behave across different snapshots because of the time variability of MAD7 for math versus the same. What we are going to do from the geochemistry side is actually computing the beta 2, both the phase of the beta 2 for different math versus the same of different black hole spin at different R high and R low. I really apologize, I cannot introduce what R high and R low means, but just practically all of this geochemistry simulation without radiation, you don't have any good prescription for the electron temperature. You actually propose some parameterization of R high and R low in which Ti divided by Te electron is actually controlled by some values of the beta and also actually the R high and R low. So here we just consider the beta 2 amplitude for different math versus the same, with actually considering low and high values of the R high and so on and so forth, just see the differences to proceed with. And then here you can also consider the phase of the beta 2. So now that was entirely from the geochemistry simulation. I wanted to tell you how much the beta 2 in terms of the amplitude and phase, because that's a complex number, would actually change, as a function of the time for different simulations of math versus the same. Now let's go to actually next step, which is the toy model. I told you that understanding what's going on completely numerically is very, very, very hard. So what we can do is actually very quickly go through this analytic ring model that, again, thanks to all of these folks that I just mentioned a few times, they did an amazing job. They actually consider studying a toy model for the polarized image of synchrotron emission from some equatorial source frame around the actually supermassive black hole, especially in Gilles et al. And then they actually consider some effects, for example, effect of the black hole spin on the photon geodesics, isolate them from some other complicated source of the effects like relativistic gravitational and electromagnetic process. And then they actually, they try to use that to get some insight for the accretion flow and space-time geometry. And more actually importantly, in their toy model, they assume to have an arbitrary, observer inclination, black hole spin, local boost, and local magnetic field. So to summarize, the ring model considers some equatorial emission near to the supermassive black hole. You actually consider some of the geometrical effects like the photon geodesic and so on and so forth. So black hole actually a spin, but disregard the rest of them because you want to be completely predictive. And you ask yourself, is this model going to be a good prescription of what full geochemistry simulation with a lot of more actually, terms into it would actually tell us? The very nice thing about these models is the arbitrariness of the observer inclination, black hole spin, local boost, and local magnetic field. Why? Because this allows us to choose any source that we want. For example, we can consider MAD7 with observer inclination of 17 degrees with black hole spin that we don't know, we can just use it for our geochemistry simulation and for local boost and magnetic field. But how I can actually proceed that? Because that really comes from the emission. The ring model proposed that you have a ring, actually the ring that is dominating, that is actually giving you the dominant source of the emission. So why we could actually use geochemistry simulation and how? That's exactly the image that I showed you at the beginning of my talk. So from the GeoMSG simulation, happily, we could go one further, and we could imagine that if I have an image in the image plane, I can just bring it back, parallel transport it back in the 3D when it's in the actually close proximity of the supermassive black hole. And I can ask myself, at every pixels of the image that I see in the image plane, where does how much of the flux density are coming from that part, next to actually in the 3D. So in this case, we azimutally average over that. We could even actually consider time averaging, and we actually consider what is the ring, because we want to put it on the ring model. What is the ring that dominates, like top 30% of the emission? Imagine that this is the emission profile, this is the peak. You actually go further and further and further down in this mountain. So we just consider some kind of like a cut of top 30% of the emission, which means that all that are actually upper than this side are just the peak, that is just like the 0%, is just like the maximum of the emission, all the way down to top 30% of the emission. If you do it, this actually circuit is going to tell you the basically coordinate of that particular ring. I'm going to use that coordinate in actually semi-analytical model that I begin with, and then just fill out this arbitrariness. And I'm going to ask myself, if I use that actually top 30% of the emission, implement it back to the semi-analytical work, and then compute the beta to amplitude and phase, is this any chances that for the entire library of GeoMSG simulation and math of saying we can get close proximity or not? If that's going to happen, that's fantastic, because we already know that ring model discriminates a lot of effects actually and just like put them aside. So whether or not we are going to capture, the most important thing is a surprise of this model. And I'm happy to tell you that, so again, this is actually what I told you in terms of where does the emission come from. I apologize, I have to be very quick here. That actually, that ring that I just told you, top 30% of the emission for math versus the same for different black hole spins. And then you can actually now consider the magnetic field and then the boost that I already told you, because the ring model has two actually content. One was the magnetic field, and then one was the velocity field. So now you see that at the location of the ring that I just described it to you, whether or not this is completely equatorial or something shifted actually, back and forth, up and down, you can actually put that coordinate, because GeoMSG simulation just give you magnetic field everywhere. So you can use that coordinate and just evaluate the magnetic field and put them in the ring model and do what you do. So here is actually the first kind of like images that we get out of it. The top actually come from the GeoMSG simulation format versus the bottom is from the ring model. If you actually look at them very closely, you see that they are doing super great for math. You can actually see that they are mostly radial here actually. They are completely doing actually clockwise for this part, or completely kind of like a circular in the other part, or actually basically clockwise for the other part, and so on and so forth. So ring and GeoMSG simulations for math are not that different. Let's just keep it in our mind. I'm going to get back to it later on, more quantitatively. But the same on the other hand, as you may actually see, they are not completely matched together. And I'm going to tell you why later on. We do have an initial proposal for doing that actually, for explaining this. So in more detail, that's exactly what I actually tried to tell you. So this is the phase of the beta 2, and this is the offset that I will describe it in a moment. So you see that when you consider GeoMSG simulation versus the ring model for math versus the same, they are remarkably close to each other. It cannot be anything better than that. So congratulations for those that actually came up with this semi-analytical work. That's super fascinating. On the other hand, when you consider the same simulation, the chances are not that much, the chances are more actually pronounced. The agreement is not very good, unless when you consider, for example, black hole spin of 0, that you consider almost 0 actually kind of like changes. And here on the bottom, delta F refers to, for example, GeoMSG simulation phase minus the ring divided by the GeoMSG simulation times 100. So you see that for the math, you are almost a order of 10% of disagreement, which is quite remarkable. While for the same, you see that you start from 25%. And sometimes I actually consider ring 1 and ring 2, because in some points, we had to consider not the top 30% of the emission location, but just go a little bit up and a little bit down. So we had to just consider them slightly actually shifted back and forth to be better matched with the GeoMSG simulation. So why this actually happens? that brings me to the end of this actually part of the talk, which actually has something to do with the impact of the Faraday rotation. As you see here for the map, when you consider the phase of the beta 2 with and without the Faraday rotation across all the snapshots that are valid in this math simulation, they are remarkably close. So no wonder that the results of the ring model could be that much actually close to the one from Geo Chemistry Simulation. On the contrary, when you consider the same simulation, especially for those that are prograde, you see that the result is just remarkably actually wrong. And that has something to do with basically with the impact of Faraday rotation. If I want to put it even in more context, it actually tells us that for the math simulation, they follow up each other. But for the same simulation, you see that even the amplitude of the beta 2 diminish a lot in the presence of the Faraday rotation. So that actually tells us that for the case of the same, we are mostly affected by the Faraday rotation for the prograde motions. And because of that, the agreement between the ring model and Geo Chemistry is not actually that good. So that brings me to the end of the second part. I wanted to very quickly tell you something that I got it out of the NGESG meeting that was remarkable actually. So that's about astrometry as a probe of the central black hole properties. So what does actually tell us? Let me just open up some questions because that's a matter of investigating more. And I'm happy that Priya is actually part of here. I'm going to tell you why. So the fact is that most of the time people are using stars that are very, very, very close to the supermassive black hole. They consider their orbits that since they are very much close to the supermassive black hole, they are going to be mostly affected by the central black hole, but not the dark matter or other actually things. And they want to consider their motion to get some sense of the black hole properties. So that's very much interesting. So most of the time, people propose to consider the shape of the stellar profile, just compute the shape in terms of triaxiality parameters, and just ask yourself what you can get out of this. So that brought me to the works that we just actually have done very recently with my collaborators using the TNG simulation. I apologize, I have to just manually make this, in which you can actually consider, the shape of the dark matter and the stars using the TNG simulation. And as you see here, in some of the cases, for example, in the middle one, there are some twists, there are some reorientation of the dark matter halo and also a stellar halo because of the fact that, actually the eigenvalues of eigenvectors of this actual inertial tensor, they just get rotated and so on and so forth. So that would be really remarkable. If we could, of course, TNG simulations are very good at something, for example, larger scale actually analysis, but they cannot be resolved at the close proximity of the supermassive black hole. And that's when the other simulations would actually come, when you can go all the way down to parsec scale. You have a supermassive black hole, you have a bunch of stars. We have a good pipeline, not only for dark matter, but also for stars. You can just use different actual techniques to compute the shape, and then you can just even go further. For example, this is some of the results that we have for a stellar halo. You really see that the twist that is actually here, you see that that's just reorienting over the distance. And this is kind of this is very common. 52% of the halo from the TNG simulation for Milky Way-like galaxies do actually consider this reorientation, actually when you go further and further out. And there is also more because sometimes they are stretching. They are more like the cigar when you're actually very close, 2 kiloparsec away from the center. But as you go further and further, that would get expanded and expanded to actually a circle or so. So again, if we could consider—
When you say halos, do you mean something that's extragalactic, or do you mean something that's really concentrated around the central black hole?
Okay, perfect. So that's a great question. That's exactly my point. The current simulation that we are using, these are for larger scale structure. Imagine that you have a Milky Way, right? This Milky Way, the video radius of that for dark matter is about 200 kiloparsec, right? So you could imagine to consider different layers, different shares of stars and dark matter, and you can ask yourself, how does it actually behave, right? When you go from inner to outer part of the halo. So this is actually the current resolution of the simulation that we have so far. Now for other simulation that Priya and others actually are considering, they get closer and closer and closer to a supermassive black hole. They are better resolved, and because of that, you can better see what would be the properties of the stars, or the impact of the supermassive black hole on their actually shape, right? So actually the stellar distribution would be completely affected or dominated by the properties of the central black hole. So something which would be remarkable actually would be to consider extending these simulations down the way to parsec each or even further down and just try to really, compute the shape. It's not hard. We have different pipelines that we can just use, and we can just like literally try to see, is this any chances that we could get that kind of actual reorientation of the halo that I just described? It's just really remarkable that it's just, changing the actual orientation, in some areas and so on and so forth. So now let me proceed very, very quickly to the last part, because that's also actually essential and important. So the next part that I would love to talk about is about the site selections for the NGEHD. These are very, very important because the NGEHD actually size and issues hasn't been actually located yet. So you could have many different locations in the globe, and you can have different combinations of that. So when you aim to consider different combination of the physics versus, for example, the image or the jet physics or whatever, the combination that you use for your sites and also the location of them would actually be different. And this is, for example, motivated by Hassan et al. In 2020, that they considered a very remarkable work in which they consider some machine learning actually analysis for how they could potentially choose their size with and without the thermal noise and also the atmospheric noise. And as you see here, again, very quickly, when you actually consider, so they consider some Ising model, they are actually correlated, different size. They can be, it's just like a ferromagnetic actually system in which you have a spin-spin interaction. They could be opposite, they could be actually, they could basically favor your Hamiltonian to be at the same orientation or opposite. And if they are positively correlated, they can be actually simultaneously on, but if they are on the negative correlation, one of them has to be actually off. So there are something related to the site activity or related to the interaction between sites. And we have a lot of different sites here. So they did a remarkable job in order to compute the correlation between the sites based on the image reconstruction, considering that they have Ising model between the sites, and then they consider some loss factors and so on and so forth, consider the image quality, and then they come up with a remarkable choice for the current site. What can be done in the extension of that is just to replace, for example, image reconstruction with the jet physics, or even add more actually into it and so on and so forth. So the room is open for many different explorations that some of them would actually need to be done from scratch. And the last part that I'm going to describe it to you, that's about the jet physics that Kaushik actually and I and others have been actually thinking a lot about this. And as I told you, the understanding the jet as very actually larger scale is not very easy. So here I'm using hammer simulation, thanks to Kaushik for doing super great job in doing these simulations. I was ray tracing them. We just consider very long jet. We just consider different blurrings here. And we are actually in the process to understand what can be done out of it. So that's actually about from the Geo Chemistry Simulation. We also have a very good and motivated PhD student, Dominique Chan, that is actually going to do a super great job for us for the semi-analytical models. So all of them are actually at the beginning, but we are going to consider different emission models and so on and so forth, just to understand what can be done. And of course, as an extension of that, we're going to hopefully consider Cora simulation from Ramesh and just consider what can be done for MAD7 for math simulation. So a lot of things are going to be done, hopefully, in the next couple of months or so. Of course, after all of the current EHG commitments are a little bit actually, reduced, but that's a lovely thing to do. All right, so, okay, apologize. This outline must be conclusion, as you see that when you prepare a slide just at the last minute. But the conclusion is that I actually told you few different directions that would be that are benefited a lot by the EHG, by the current EHG result or the NGEHD in terms of the science and in terms of design. So if I want to go through them in 1 minute or so, we started from jet for the positrons. We just consider that observationally, since we know that we have a long jet, and since we know that the current models are not sufficient in order to have jet that is powerful enough at very long distance from the center, we may have to add something into it. Pairs could be one possibility, but these are not very actually easy to do. We consider two approaches so far. One is completely semi-analytical, while the other is just considering actually geometry, adding the positrons there, considering some maps and so on and so forth, the work that Richard is actually leading. We went further and just considered the link between the magnetic field geometry and the ring model that some folks actually figured out. We got remarkable agreement for the mass simulation, but not that good for the same one. We went further to NGEHT. So from here, you're done with the EHT and you go to the NGEHT, in which you can consider the astrometry of the stars to get to the actually black hole properties. Hopefully we are going to do a good job considering newer simulations, very much focused to the actually black hole and very much resolved to see what we get. And finally, the design that are super important, because if you are not that good at your design, you are missing a lot of physics. So I'm very happy that there are a lot of remarkable people that are working on this, especially Alex and actually Shem and others, in which are doing a super great job in order to optimize this kind of site sampling. And then if you do it super great, then no wonder that you get more and more in the next actually generation of the ESG observation. So that brings me to the end of my talk. Thank you so much for your attention, and I'm happy to take questions. I apologize if I was a little bit long.
All right, Razieh, thank you very much for an outstanding talk. We have time for a couple of questions for you.
I have a question. So
Sure.
very interesting stuff, Razieh. So we asked a question about different wave bands. Maybe thinking 345 or something like that, higher frequency, and you can go lower in frequency. There's the possibility of, for the next generation instrument, tuning the receiver. So if you had a 230 gigahertz receiver, you could conceivably go all the way up to 270, even 280 with a flexible local oscillator.
Right.
But that's a relatively inexpensive thing to do. So it'd be interesting to start thinking about what one could do with sequential observations all across that band.
Yeah,
To
absolutely.
look for Faraday rotation or other kinds of.
No, absolutely. Yeah. That's a super great suggestion. Thank you so much for bringing this, because some analytical models are not that expensive in changing the frequency. What Richard is doing could be a little bit more expensive because you have to go to GRMATI, for example, or whatever. That is a little bit actually more expensive. But for the semi-analytical works, you can just go and consider. So I think that will be remarkable just to consider the spectrum at different frequencies and just try to see what we get, according to the current result, or even as a prediction or proposal for NGEHT. Yeah, absolutely. Finger crossed. Yeah.
Very nice thing.
Sure.
Very nice talk, Razieh. Oh my God, you're doing so much, putting a lot of us to shame, a number of projects.
Oh no.
So what is a related question, right? So suppose the question you wanted to settle was the positron fraction in the jet. What is the ideal data set, like beyond M87? So I'm curious, right?
Okay.
So what is what are generic jet features that you would want to extract that would be useful to understand more than an individual object?
So that's a super great actually point. Again, Shep is here, so I have nothing to say, but let me just tell you actually, let me at least show you some of the observations which are actually listed here. So this works of using actually different sets of observations, including VRBR observations, linear or secular polarization, or even emission line. They consider different types of actually observation that are at different, different sources at different frequencies. For example, I started saying that you have M87, 3C279, 3C345, for example, 3C120 and so on. So that would be remarkable to collect all of this data actually, and just try to see what you can actually get out of them, right? But again, that would be on the extension of what we have considered. So I wish I had a slide for 86 gigahertz that we considered, but you can consider diminishing the actual frequency. That's not very expensive. In GR trans or iPod or whatever, actually, you can just play around with the frequency to begin with, and you can just consider at different sources. Of course, when you change to this 3C120, what you need is actually also to refix the B naught, right? Because the dimensionless magnetic field that I started with, that actually depends on the flux. So that's entirely depending on source that you consider in terms of the distance, in terms of the flux, and so on and so forth. So yeah, for that, we really have to have some VLBI observations that tell you, for example, on this 3C120, what is the flux? and so on, what is the distance, and so on and so forth. So if you could do it, and I wouldn't be surprised that they already have it in some of the papers that are being actually written or have been already written by this, by this VLA or actually ESG or whatever,
So
that
the
we could just
spectral
use
shape,
that.
the spectral shape, the general spectral shape must be available, right? For
Yeah,
these multiple
absolutely. Yeah,
sources.
if you want to have some predictive results, because your MSG simulations are scale-free, you can almost scale it to anything you want, even a stellar mass black holes that we are thinking with Cauchy. But the fact is that when you want to consider that, you have to have a well-defined flux and the locations, and that's all. If you have these two parameters, you can just either freely scale it back and forth, up and down in terms of the B naught, and just recompute the images. You can just go further, compute the actually spectrum, and so on and so forth. Does that answer your question? Or?
Yes, thank you very much.
Sure. Yeah, Richard,
I just
please.
want to add a little bit to Sweet's question. So positrons tend to cancel intrinsic circular polarization, and they would do so on their own devices if it weren't for Faraday effects. So if we have a jet model where we could make these maps and we have the other polarizations than circular tell us that it's a reasonable jet model, and then we see in the circular polarization a very low degree of circular polarization. If we could resolve the circular polarization on the scale of tens of gravitational radii, then that would be one of the smoking guns for high positron fraction. And also, in order
Generically, right?
Yeah. Yeah, and also, if you wanted to verify there were Faraday effects or not, you could see if the time-dependent electric vector polarization angle is doing those rotations that you were seeing in those movies or not. Because if you have a very Faraday thick material, then the electric vector polarization angle is actually proportional to the Faraday depth. But the Faraday depth changes very sensitively in the positron fraction. If you increase positron fraction by just 1%, for instance, you'd see a noticeable change in the electric vector polarization angle if your material is Faraday thick. However, in the other movie where you didn't see any change of electric vector polarization angle, even if we took the positron fraction from 0 to 100%, then that's a material that's not subject to those Faraday effects. So that would be something where you could make the implication that if you are seeing a circular polarization pattern that completely cancels, then the Faraday effects would be ruled out. Plus, you'd be able to conclude that there's high positron content.
Thank you.
Sure. Thank you so much for all of these fascinating questions. Shep, do you have any comments about different sources? I think Yeshi did also a great job in actually probing other sources. Well,
well, thanks for putting me on the spot. my next talk, in the next hour, I'll be speaking. Well, maybe two quick comments. One is that of course, looking at these jets on larger scales is extremely important. And these papers are very well known. And there's a long history of looking at the content of these jets. But another interesting thing to think about is in the context of the ring models that you were looking at, those have few parameters. So you could start thinking about putting M87 5 times farther away and modeling what that would look like and seeing if you can extract with some robustness the kind of parameters that go into the simulation.
Yeah.
The key thing is that going farther out gives you an R³ factor in terms of the space that you're sensitive to. So you could increase the number of black holes, which you can model the shadows.
Interesting.
By just using ring pits.
Yeah.
That's one thing that I know that Gabriel Broderick has done some of that. So just saying that there are a number of different ways to add to the.
Sure. No, that's amazing actually, because the current setup for IPOL, you can just easily scale them, back and forth. The only thing is that the flux, should it be exactly the same flux that we use for here, like 1.5, Johnsky for M87, or shall we also scale the flux down as a distance to, whatever, like, if this is a distance, actually, if this is a, density 1 over R³ or whatever, that's the things to actually think of it, but yeah.
Yeah, of course, if you only have a lower flux density, Don actually just wrote a paper on the expected number of shadows we would see.
Yeah.
There's some very useful relations in that.
Okay, very great. Yeah, absolutely. Yeah, because of the cosmological factors and so on and so forth. All right, yeah, there are a lot of things to do. If you guys are interested, please join us. We need human power, and yeah, that's that's like.
All right, so I think it's time to wrap this up. Let's make another round of applause.